Good. All right, so what do they mean? If they say this relation is reflexive or this relation is transitive or symmetric. So let me just give a short or a simple example that will help us understand. So imagine that we have a relation between the first set there. Maybe we have 1, 2, 3. And then you also have another set there, which is the set of outputs. You also have 1, 2, 3 there. So this relation will only be said to be reflexive if there exists in the solution set, or in the, yeah, let me just say in the solution set of this relation, if there exists elements 1, comma 1, then apart from that, maybe you can also have something like 2, comma 2. Then apart from that, you also have 3, comma 3. So if any of these relations are missing, then we do not, then we say this relation is not reflexive. So reflexive, the word itself, reflexive, is from the word reflect, meaning it's something that has to do like, that has to do with a mirror like. Yeah, so what it means is that if, let's say for instance, we've been given a function y is equal to, let's say 2x. So if after putting the input there in this value of x there, the answer that you get is t1, then and then after putting 2 there, the answer that you are getting is 2. After putting 3, the answer that you're getting is what? Is 3. If this relation is giving you these solutions, or these solutions are part of maybe the solution set, it means that the given relation is reflexive. And what does it mean when we talk about the symmetric? Yeah, so for symmetric, it's for symmetric, the what's this? For symmetric, you pardon me, I'm not feeling too well. Yeah, I'm sure for those that texted me yesterday, I told you the reason why we never had class. Okay, so for reflexive, if let's say for instance you've been given any relation or any function representing a relation, reflexive means that for any for any given input, let's say if you've been given 1 as the input, and then the answer that you get there is 2. So within the same solution set, if there exists another a relation that is going to have 2, comma 1 as a set of a set of the input and the output, this implies that the given relation is what? Is symmetric. That's what it means. So if you have maybe after putting in 3, the answer that you're getting is 4, or after putting in 4, the answer that you're getting is 3. If you have these two in the same relation, or in the same solution set, it implies that the given relation is what? Is symmetric. That's what it means. Then when we talk about transitive, so this one is a bit tricky. So for transitive, what you need to understand is that if you have, let's say, after putting in 1 there, the answer that you are getting is, let's say you are getting 2. If after plugging in 1, the answer that you are getting is 2, and then after plugging into, the answer that you're getting is 3, and then you also plug in 1, this same one is also giving you another solution, which is 3. So that relation is said to be transitive. So the simplest way you can explain this is that if you have the first element there, this one gives out the second element, then the second element is also capable of giving out the third element. But this first element is also, if it's also able to give you the third element, it means that the given relation is what? Is transitive. Yeah, so it's as simple as that. So let us try to look at some of these questions and how we can apply what is the explanation that I'm just from explaining. Okay. So the question says, determine whether each of the following relation is reflexive, symmetric, or, and transitive. Relation R in a set A. Okay. So you have the set A, which is equal to 1, 2, 3. So this goes up to 14. So you have 4, you have 5, you have 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, so this is the first one that has been given. And then defined, so the relation R in the set defined as R is equal to X comma Y. And for every value of X minus Y, the answer should be what? 0. So what do they mean when they say that? So if you want, you can take this Y to the other side of the equal sign so that you have the value of Y being equal to what? 3X. So now, they are saying in a relation, so they are saying the value of R is equal to X comma Y such that 3X minus Y is equal to 0. So the value of R, so let's find the solution set for R. So how do you find this? This is as simple as drinking water. So let's try to find what R is. Okay. Okay, so let us see. Um, yeah, so let's find the solution sets. So the solution set, according to this equation there that we've been given here, you can say when you replace 1 there, the answer that you are going to get is what? Is 3. So this is our first set. Then the second set, if you replace 2 where there is X there, the answer that you are going to get, so if we replace 2, the answer that we'll get is 2 times 3, that will be 6. And then the other one will be, if we replace 3, we're going to have 3 times 3, that is 9. If we replace 4 there, we're going to have 4 times 4. 4 times 3, the answer is 12. So we have 4, comma 12 there. What if we replace 5 there? When we replace 5 there, the answer that we're getting is 15. But 15 is not part of this given set there. So we just end there because our solutions are not supposed to exceed what we've been given there, which is 14. So now, this is our set. So let us try to determine whether this set is transitive, or this relation there is transitive, symmetric, or reflexive. So do we have anything that is, let's say for instance, 1, 1, do we have something like this? Do we have 2, 2 there? Do we have 3, 3? Do we have 4, 4? So when you check these solution set that we have, we do not have any of these. And as a result, we can say the relation is not, it's not reflexive. So the relation is not reflexive because we don't have any of these. And let us see if this relation is symmetric. So if you check, we have 1, 3 there. Do we have 3, 1? The answer is no. We have 2, 6. Do we have 6, 2? The answer is no. We have 3, 9. Do we have 9, 3? The answer is no. We have 4, 12 there. Do we have 12, 4? The answer is no. And this tells us to say this relation is also not symmetric. We move on to transitive. So how do you determine whether the relation is transitive or not? Remember what I said. For transitive, you always have to understand that if you have any element or any input, if their output is B, they are also supposed to exist the input B giving out what? Giving out the output C. And after that, we also need to know that the input A should also be able to give out the output what? C. If you have anything like this existing in this solution set, then you conclude and say the solution is what? Transitive. But let us try to check if this is if this is available in this given set. We have 1, 3. Do we have 3, 6? Rather, do we have 1, 3 there. If I take 1, 3 there, do I have anything that is maybe 3, okay, we have 1, 3. Let me write it here. We have 1, 3 there. So we have 1, 3, and then this 3, what happens if we replace it with this x? We're getting what? 3, 9 there. So we have 3, 9. So now, do we have another solution that is that is going to give us, or where we're going to put the input 1 and get the output 9? If we don't have, then the relation is what? Is not what? Transitive. So if in this solution set we had anything that was maybe looking like 1, 9, if we had any if we had this set also part of this set, would have concluded that the given solution or the given relation is what? Is transitive. But in this case, we don't have 1, 9. And as a result, 1, 9 is not a member of what? Of R. And this tells us that the solution is what? Is not transitive. Okay. Let's move on to the next one. So the next question is, so we have the relation R is, in the set of natural numbers. So this one we've not been told what's this? Oh, there's this one here. There's a condition that these natural numbers, the inputs of x are supposed to be less than 4. So meaning the inputs of x that we have are going to be what? The inputs of x that we're going to have are going to be 1, because we know that natural numbers are counting numbers starting from 1. So we have 1, 2, and 3. These are the inputs that we have. So now we know to say the solution set here should contain what? Or the outputs should be also natural numbers. Yeah, so the outputs should also be natural numbers. All right, so let's quickly move on to finding the solution set R. Yeah, the set that contains all the minor sets. So R is therefore going to be, we open brackets. So if we plug in 1 in this given expression there, which is y is equal to x plus 5. If we put 1 there, we're going to get 6 as the answer, because that will be 1 plus 5. So 1 will give us what? 6. And if we put 2 there, 2 will give us 2 plus 5. This is going to be 7. Then if we put 3 there, 3 plus 5, this is going to give us 8. So this is the solution set that we have. And now the question comes in to say, is this relation reflexive, symmetric, and transitive? So we need to check, we need to see if it's reflexive. So do we have anything that is 1, 1, or 2, 2, or 3, 3? We don't have in this relation. And that tells us to say the relation is not reflexive. So the relation is not reflexive. So apart from that, we also need to determine whether it's symmetric. So how do you determine whether it's symmetric? So you also have to do what? So determine whether it's symmetric or not, you need to check whether whether there is something that is maybe if, for instance, if you have 1, 6, and you can just check 1, because if this exists for 1 and doesn't exist for other numbers, then it's still not symmetric. So if there is 1, 6, do we have a 6, 1 in this relation? We don't have. So now, since 6, 1 is not a member of the relation R, then the solution is also not symmetric. Okay, let us also see if the solution is transitive. So how do you check whether the solution is transitive? We also have to check if, since we have 1, 6 there, do we have 6, another number this side? So we don't have anything that is starting with 6, and then giving another number, because if you put 6 there, yeah, if you put 6, anyway, we're going to, okay, if you put 6 there where there's x, the answer that you're going to get will be 11. So we're going to have another solution set like that. But according to this given condition there, the value of x should always be less than 4. So putting 6 there is not one of our solutions. Hence, this tells us to say the solution is also not transitive. I mean, the relation is not transitive. Okay, let's look at C. So for C, we have the relation in the set A being equal to that. So the set A has been given that, like it's given in that way. And then R, according to them, they're saying R should be in the form x, y. And then in this case, y is divisible by x. So y is divisible by x. So since y is divisible by x, this tells us to say it's possible for you to find x, x in this expression. What do I mean? So what I mean is that it's possible for you to find 1, 1, because 1 is divisible by 1. They are saying y is divisible by x. And it's also possible for you to find 2, 2, because 2 is divisible by 2. It's also possible for you to find 3, 3, and because 3 is divisible by 3. It's possible for you to find 4, 4, 5, 5, because 5 is divisible by 5, 6, 6, because 6 is divisible by 6. And this tells us to say the relation R is reflexive. And
I haven't understood on this one.
here they are saying y is divisible by x, meaning any value of x that you get in this one should be divisible by the other. So it's possible for you to find 1, 1 in this expression, because the condition here is y should always be divisible by what? By x, meaning x can go into y. So the values of x that we have are the ones that we've been given there. This is the domain that we've been given. So these are the inputs that we've been given. So they are telling us to say this input, for every input that you want to use there, the output should be divisible by the input. So if we have 1 there, it means that we can write 1, 1. It means that x, comma x is a member of what? Is a member of R, because for every value of x that we get, we can find another value in this same set, which can, where this x can go into without leaving a remainder. And as a result, you find that 1 can also go into 1 without leaving a remainder. 2 can go into 2 without leaving a remainder. 3 can go into 3 without leaving a remainder. Yeah, so this is one of our, this one tells us to say the relation that we've been given here is what? Is reflexive, because for reflexive, for every number that you have in the domain there, you need to have um you need to have um you need to have x comma x being a member of the of the relation, or you need to have I'm sure you saw what I wrote. For every you need to have a comma a. If you have, let's say the inputs are A, B, and C, you need to have A, comma A, B, comma B, and C, comma C. So once you have, if this is your set of inputs and you have these as your, and you have these as part of your solution set, then the given relation is reflexive. So let us see if this relation is symmetric or not. Okay. So we proceed. Let's check if this is symmetric. So let's take any number in this set of inputs. Okay, what if I take 2? So if I take 2, I'm going to say, remember, for every domain, or for every value of x that we get from this domain, the value of y should not be the value of y. Okay, let me just say we need to get the domain from the given set, and then the range there doesn't really matter, because the relationship, oh sorry, the range should also not exceed the what is the relation, or not the relation, the what is the solution set that we've been given. Yeah, it should be within this given set. So what I'm trying to say is that if I get something like maybe a 2 and a 4, because I know if you want, you can get 3 and 6, because 3 and 6 can divide according to the relation that we've been given there. So if I decide to get 2, I know to say 4, 2 can go into 4. How many times can give me 2? And then can 4 go into 2? The answer is no. Yeah, so according to the relation here, we said y should always be divisible by what? By x. So of course we have found that 4 is divisible by 2, but is 2 divisible by 4? The answer is no. And as a result, we conclude that the given relation is not symmetric, because in the solution set of this, we have 2 comma, so we have 2 comma 4, but we do not have 4 comma 2. why don't we have 4 comma 2? It's because 4 is, 4 is, sorry, in this relation we have 4 comma 2, but we don't have, oh, I think what I wrote was just okay. I'm trying to process. Okay, so I wrote this. I said in the solution set of this relation, we have 2 comma 4, because remember they said y should be divisible by x, so y should be divisible by x. So meaning 4 in this case is divisible by 2, meaning we have this in the solution set, but we don't have this because 2 is not divisible by 4. And since this is there, this is not there, this tells us to say the relation is not symmetric. So if the relation was to be symmetric, 2 comma 4 was supposed to be present in the relationship, rather in the relation, and then 4 comma 2 was also supposed to be present. But in this case, we only have this one. We don't have that. Okay. So now, how do we test if this relation is transitive or not? So to check whether the relation is transitive or not, for this one, they are saying for all values of x, I mean, they are saying y should always be divisible by x. Okay, let me just erase everything. So they are saying y should always be divisible by x. So now, to determine whether this relation is transitive or not, you can try to get, let's say for instance, you get any number that is, okay, let me just use letters. If you get any number that is x, meaning you're getting any number from the domain there, then the answer that you get there, it gives you y. And then if you replace the value of y in this same expression, in the same relation, you are getting the other solution, which I'm going to denote as z. So as long as x comma y and z and y comma z are members of the solution set R, this tells us to say it's possible for you to also find it's possible for you to also find what it's possible for you to also find x comma z in this expression. So this is also going to be a member of the relation there. Hence, this one is transitive. So what I mean is, let's take, for instance, we get 1. So if I get 1 there, if I get 1, I'm going to say 1 divided by, or if I get 1, I'm going to say 1 divided by 1. The answer will be 1. So this same y that I've gotten here, I'll say again y, which is my 1, divided by 1 again. I'll still get my z as what? As 1. So this same 1 I'm going to get there. If I say, because here we're dealing with division, for any set to qualify to be part of this relation, it has to, it needs to be, I mean, y needs to be divisible by x. So if I get this as the value of z, I can also get 1 and say this same, I can get this one that I had this side and say this same one, is it divisible by the value of z there? If the answer is yes, then this also qualifies to be part of our solution set. And hence, we say this relation R is what? Is transitive. Okay. So I'm recording the session in case maybe what I'm explaining is not, you're failing to understand. You can watch the video for the second time immediately after the lesson, so that at least maybe you may get one or two things. Okay, so let's do the last part of this question. So the relation R is a set of integers defined by R, x comma y, which is x minus y. So x minus y is an integer. So x minus y is an integer. Okay. So if x and y are integers, and when you subtract x and y, the answer that we're going to get will still be an integer. Okay. So when you check the set of when you check this solution set that we've been given there. So according to the solution set, they are saying these are solutions that we are getting are supposed to be integers. So when you subtract x minus 1, when you subtract two integers, the answer that you always get is still going to be an integer. Yeah, when you subtract two integers, the answer that you get will still be an integer, meaning they are in the same solution set. And as a result, we can say this given expression is reflexive, because for reflexive relations, the most important thing that you need to get there is, if what you get there is part of the solution set, the answer that you are supposed to get there is also, okay, let me just do this. Okay, the link is about to end, so we'll have to join using the same link so that we finish up the remaining part. So if for reflexive, we need to have a comma a there being present. If, for instance, we have a, b, and c as part, as part of the domain there, then b comma b should also be part of our solution. Then c comma c should also be part of the solution set. So in this case, what we've been given is generally just integers. So meaning whatever that we get after subtracting these two, if it's also going to be an integer, it means that it's in the same locality. I mean, the value of y the value or the answer that we're going to get will be in the same locality